In this video, let's look at how to determine the significant figures and digits of precision for a linear function. So in chemistry, especially in first year chemistry laboratory, Beer's law is often a lab topic. In Beer's law, what you're doing is you're measuring the absorbance level of a solution compared to its concentration, to its molarity, and building a calibration curve, a best fit line here, to determine the concentration of an unknown solution, or the absorbance of a known concentration solution. And one of the most challenging things for students often to do is to determine how many significant figures or digits of precision to put in the slope of that best fit line equation, or the y-intercept, because this is just the slope-intercept form. So this is just y equals mx plus b. But you know, on your software, your graphing software, or graphing program, it just gives you the y equals mx plus b equation, and it often doesn't account for significant figures or digits of precision. So how do we determine those? Well, in our y equals mx plus b equation, m is equal to the slope of the line. Okay, and if we remember, slope is equal to that change in y over change in x. So when we look at this operation, this is simply a division, is what a slope is. It's a division problem. Well, in division, the answer has the same number of significant figures as the measurement with the fewest significant figures. So if we look at our y-axis here, we see that we have one significant figure here. Now some of these have two, but remember, we can't be more significant, so to say, than our least significant. So our y-axis has one significant figure. When we look at our x-axis, we see the same thing. We see that our x-axis has one significant figure in those values. So we have one sig fig divided by one sig fig. So our answer would be rounded with one sig fig. So this would turn to y equals 4x, okay, because we do our rounding, plus, now let's take a look at the b. The b value, remember, is equal to your y-intercept in this equation, okay, the y-intercept. Well, the y-intercept, okay, we've got concentration here on the y-axis. So a y-intercept, it's a value. We should use the same number of digits of precision as that's plotted on our y-axis. Okay, so the y-intercept, those sig figs, we look straight at the digits of precision on the y-axis. Okay, on the y-axis, it looks like we have one digit of precision here. Let's make this 1.0 so we have consistency. One digit of precision, so our answer should have one digit of precision. And in this case, it's kind of unusual. It would be 0.0 because this one doesn't cause a rounding up scenario. So slope is a division process calculation, so we look at significant figure numbers, and y-intercept is based off of the plot on the y-axis, so we look at the digits of precision. So let's look at one more example. Okay, here's our data, and here is the graph before we do the linear regression to get the best fit line. So let's just determine in our y equals mx plus b equation how many significant figures for the slope. Okay, remember slope is a division of the change in y over the change in x. We can see that our y values here have 4 significant figures, 4 significant digits. Our x-axis looks like those have 3 significant figures. So when we do our division of 4 significant figures and 3 significant figures, we go with the fewer. So our slope here, our slope m, will have 3 significant figures in its recorded value. And then let's look at the b. The b is the y-intercept. Okay, so we look at the y-axis and we notice that there are 4 digits of precision. Okay, I'm going to put DOP, digits of precision. So when we record our y-intercept, we would take it to 4 decimal digits, 4 digits of precision.